Today we will be talking about similar figures. In this lesson, you will be able to name corresponding angles and corresponding sides of similar figures. You should already be comfortable with doing corresponding angles and corresponding sides of congruent figures. We're going to identify similar figures, and then we're also going to find unknown measures of similar figures. A similar figure are figures that have the same shape, but not necessarily the same size. So what this means is our angles are going to be congruent. Notice we have these congruent markings at angle B and angle E. A is congruent to angle D. C is congruent to angle F, which is said down here. So the angles are congruent, but the side lengths are not. Visually, we can definitely see that side AB is not the same length as side DE, but those sides are proportional to each other. Or in other words, there's some rate, or we'll call it a scale factor, that we can go from side AB to side DE, or vice versa. Maybe we're enlarging or decreasing. So we'll have this proportion or this ratio in order to figure out are these figures similar or not. And for our similar symbol, we're just going to use that squiggly line. So when we talk about similar, they're not congruent, so we can't use the equal and the squiggly line like how we do here. These angles are congruent, but the triangles are only similar, so you just use one little squiggly. So let's look at a couple examples to see if these polygons are similar to each other. So you're going to want to have a calculator when doing this because we're going to set up some ratios and see if they are equal to each other. So in the first one, we're going to look at, and you'll want to kind of glance at and say, okay, well, angle C and angle G are congruent. Here I notice B and F are congruent. A is congruent to E, and angle D is congruent to angle H. So my angles are congruent to each other, so that is one thing that you do want to check to make sure. And then I'm going to look at those corresponding sides and make a ratio for it. And it doesn't matter if I start with my big polygon and move to my small polygon, or if I start with my small polygon and move to my big polygon, as long as I'm consistent with all of my ratios. I tend to go left to right, so that's how I will go here. So I'm going to look at side AB, has a side length of 5, and the corresponding side EF has a side length of 2.5 or 2.5. If I go 5 divided by 2.5, I would get 2 as an answer. Now I would want to double check all of my other corresponding sides as well. So I'll do side BC is 6. That corresponds with side FG, which is 3. That's also 2. Side DC is 7, and side HG is 3.5. That is also 2. And then also finally AD is 4, and side EH is 2. Again, reducing that would be 2. So yes, these polygons are similar. They have congruent angles and proportional sides. Number 2, visually we can definitely tell that their markings on their angles are congruent, and then you would want to double check your corresponding sides. So again, I'm going to go left to right. So I'll start with DE is 4, and then HJ would be 5, so that is 0.8. And then I want to double check all the rest of them to see if that would also be 0.8 or 8/10. Why don't you pause the video and see if all of the sides do have the same ratio. So after you have paused it, you should have double checked all of it, and hopefully you did get that they were all the same. So let's just double check here. So I have DF is 3, and that corresponds with 3.75. And when I plug that into my calculator, I do get 8/10. Now my last side is side EF, which is 5, to side JK, which is 6 and 25/100ths, and I also get 8/10 there. So again, yes, these are, give give myself a little bit more room. Yes, they are. They have congruent angles and proportional sides. Of course, the corresponding angles and corresponding sides. Now, if we are looking at number 3, visually, I would look at those angles, and those are definitely congruent to each other. They're all 90 degrees. And then I would notice, okay, well, these guys are both 3s. So that would be, if I were to divide it, 3 divided by 3, which is just 1. And then my other one is 5 divided by 3, which is definitely not 1. So no, they are not similar. Because they don't have proportional sides. The last thing that we're going to do is find the missing angle measures. So these polygons are similar, so they do have congruent corresponding angles, and they have proportional corresponding sides. So we just need to set up two ratios or two proportions equal to each other and solve for our missing side length. So for example, I could take any one of them that I already know. So in this case, I know over on my right-hand side that FG is 6. FG goes with BC, so I'm going to go and write 6 over 9, and that proportion must be equal to the other sides. In this case, I want to find out what X is, and X, or side HG, corresponds with side DC, or 12. So I would write X over 12.
These two ratios are equal to each other. That's what the equal sign means. So what we want to do is we want to try to figure out what number we can put in for x that is equal to this ratio or this fraction, or we can also call this scale factor over on this side. And there's a couple ways that we can do this to make sure that we fully understand that these ratios are equal to each other. We can understand that there's a relationship between this part to this whole, and maybe we might see a connection right there, and we can follow that same connection here. That's called a vertical relationship. Or we might see a horizontal relationship in that maybe we multiply or divide by the same number here, and then we can follow suit and go do the same thing here. Because it's either going to be bigger or smaller than our original ratio. In this case, these numbers are going to be bigger. 9 is smaller than 12, so this number right here is going to be bigger than our 6. Well, I don't see like a pretty straightforward, without some decimals, I guess, going on, relationship here. But I do notice that this can be reduced. 3 goes into both 6 and 9. So that's what I would do in this problem, is I would divide 6 and 9 by 3 to get that 2/3 equals x over 12. Now I can easily see that 3 has a relationship with 12, or in other words, I can go 3 times 4, and that gives me 12. Equally, I can do that on the top, and I will have an equal proportion and know that x equals 8, because 4 or 2 times 4 equals 8, and those ratios would stay equal to each other. Again, I could come over to the side and I could check, like how I checked how I did the last problems, and go 8 divided by 12, and that does reduce both of them by 4. And so that gives me 2/3, which is that same ratio that we reduced right there, that 2/3. So my answer for number 1 is that x equals 8. Let's look at number 2. So in number 2, I would set up my ratios, my proportions. And I would see that GJ, which is 2, has a corresponding side to LO, which is 3. And that's going to equal JI would go with M. So it doesn't matter where your variable is, whether it's on the top of the fraction or the bottom of the fraction, you'll be able to see a relationship either way. So in this case, I can't reduce my 2/3 here, and I don't really see a quick relationship between 2 and 3 vertically, but I do see a horizontal relationship. I see that 2 times 2 equals 4. So in other words, this ratio right here is just going to be double this ratio right here. So all I have to do is times the bottom by 2, and I get that M equals 6. So again, I could kind of check to make sure that that ratio on my new corresponding sides that I filled in, 4 divided by 6, that does reduce to 2/3, which is that same ratio right here of 2/3.
Don't forget to do your summarize. Also in there, if there's any questions that you have, go ahead and write it in with your summary. Answer the question on the bottom. If the figures are similar, explain your reasoning, so why or why not.